Hi class, today we're going to talk about the volume. There are two methods that to find the volume, and that's for different cases. One is known as the disk method, and the other one is known as the washer method. And so we're going to talk about those two approaches, and then finding the volume of a solid with known cross sections. So just want to give you guys a quick recap. What does it mean to be a volume? If you have a three-dimensional object, the space covered by this three-dimensional object will be the volume of the solid. All right, so what is the disk method? Well, if you guys think about a disk, right? A disk looks like this, right? And a disk, it might be a disk where it has a little width in it. So you can kind of see that this is sort of kind of describing that disk. The disk does not have a hole inside. It's just pretty much a solid space, right? There's no holes. It's just pretty much that. Now, that means that the disk is sort of kind of like a little cylinder. There is a radius of this. We can call that R, and there is a width for this. And we know how to find the area, the volume of a disk, right? We know that the area of disk is, if you think about it in the form of a cylinder is going to be equal pi r square times the height. Well, in this case, the r is big R, pi is pi. In this case, the height happens to be the width of this disk. So we can see here that this the volume of this disk can be translated as pi r square W. So the concept of finding the volume of a solid, such as if we have this solid right here, is the concept that we can just add a bunch of disk, right? If you add a disk here, and then add another disk, and then add another disk, and then add another disk. And so you're just adding a bunch of disks, right? If you think about it, you're just adding a bunch of disks, adding a bunch of disks, adding a bunch of disks. And so this disk have some kind of volume, and sort of the idea that you're able to find the area on the curve by adding rectangles, right? By just adding rectangles. Well, obviously here this is a solid, so therefore we're adding disks, right? So the idea is that we're adding n number of disks. This will give us a nice approximation of the volume, right? Because this is still just an approximation. There's going to be some error there along the way. There's always going to be some error, right? But obviously, what we can think about here is that this can be done. This approximation can be done by using the volume of solid of a disk. So it is a very similar concept as before. So we want to keep a few things in mind as we're going through. We want to keep in mind the radius of the disk, right? The width of the disk, and the fact that this disk happens on the axis. This axis is going to be consistent, the same axis for every single disk. This axis is sort of kind of important because that tells us where the position of everyone is. So this is known also as referred as the axis of revolution. The axis of revolution. So we can think about that the revolution is revolving this disk in this axis. So we said that that means that the approximation volume of this can be described as pi r. This is as pi r square delta x, right? This is the volume of each of the disks, right? This is described as the volume of each of the disks. So if we extend this concept and we try to take the volume of this is how we can approximate it if we have n disks, right? But obviously we already know that from the Riemann sum that we can extend this to have n infinite rectangles. We can have infinite disks as well. So the volume will then translate to this form, right? From the volume of a disk to the representative element of the disk, right, into something of this form. So pretty much this is coming from here, that pi, as is important it is, right? Here's our volume of the disk. Pi is just a constant that will be factored out. So we're just doing this for n disk. As n as the absolute value of delta goes to 0, that means n is going to infinity. So that means that what we're going to have here is the Riemann sum of this, which will be equivalent to the integral from a to b of r of x squared. So there you go. So we know where this is coming from, and so now we can sort of narrow down the approach by automatically applying this formula. So we know where it's coming from. We know that it's always going to have a pi, right? And we know that we're going to go from a to b, and then we're going to have some radius, and we're going to square the radius. We know sort of the elements of where this is coming from. All right, so we're gonna figure out where this is rotating, right? Because what we're gonna do, this is gonna be important. If you think about it in here, we need to figure out this axis, because that will tell us how big is our r. So this axis and the radius of the disk will tell us what the r is. So it's important for us to know what is the axis of rotation. That's where we're gonna start. So we know the axis of rotation is here. So that means we can figure out the radius of the disk, right? And then what we're going to do is we're going to rotate that, and that will give us the disk, right? Now we are still going to have boundaries from a to b, and then we have still delta x, right? So that translates to this in respect to dx, right? Because delta x is changing this way. Now, if we decide to do it in a different perspective, in using the horizontal approach of vertical axis revolution, so if we have this, if we know that this is the axis revolution, then therefore we're stuck using the vertical approach. We're stuck, right? There's no other way. So we can think about that. Hey, we can figure out the height by just looking how far is this to the axis, and then figure out what are the boundaries, how far we can go, right? So this is your delta x. We're going to figure out, your delta y. So we're going to figure out how high can we go, and those are be the boundaries, just like before. And then so that gives us a very similar formula, very consistent. So there you go, right? So let's go ahead and use this formula to find the volume of this solid. Using the disk method, find the volume of the solid formed by revolving the region bounded by the graph f of x equals the square root of sine of x, and the x-axis between 0 and pi. So if you notice here, they're telling us that we're gonna bound this solid is bounded by this in this, right, and this right here. But we're gonna revolve in the x-axis. But if you guys notice, there was no such thing as, they didn't say you're going to revolve on the x-axis, right? But they use the word about, and about will be the key word. This is the key word, right? This is the key word, because that will be the language that we're going to be using to tell the reader that you are rotating on the x-axis. That's it, right? It's very subtle, right? Just the word about. So that's sort of, sometimes students will forget that that's how we translate the rotation. So anyways, so we're gonna use the function f. We're gonna use this, and then we're gonna rotate around x-axis. We know how far we're going, from 0 to pi, and then so we already know the boundaries. This is your a, this is your b. You know what's your function, and so you know what the radius is, right? The height of this radius is going to be this function. So therefore we have rx equals the square root of sine of x. So we're going to set up the problem, pi times the integral from a to b of the square of rx. This gives us pi times 0 to pi of the square root of sine of x square dx. Those cancel each other out, so you're left with sine. The integral of sine is negative cosine. We carry the pi, don't forget about the pi, and then we evaluate from 0 to pi. Now here is a different approach. We can think about that this is being multiplied to whatever this is going to be. So sometimes I like to do that just to keep it more simple. I left the pi outside, and then I evaluate it using this, and I evaluate it using that. if you guys think about it, it's the same way, right? It's the same thing if I would have put the pi in front of each one, right? So it's a nice, sometimes it's nice to keep it like that. That way you're not overwriting this number, even, and it's sort of simplifying, it's allowing us to simplify this much quicker. Negative cosine pi is negative 1, minus cosine of 0 is negative 1 with a negative in front of it will give us a positive. So you have pi times 1 plus 1, which is 2 pi. So 2 pi is the volume of this. And that's it, right? We're able to find it that simple, right? And if you guys think about it, it's sort of very consistent with what we did with the area. But we just have to do a quick setup. This and this are the two different things. All right. Anyway, so that's finding the area, the volume of the solid. Remember that these units will be units cubed because it is a volume. All right. So the washer method is very similar. It's sort of an extension of the disk method. If you guys think about a washer is and this comes from the tools of if you have if you try and put a screw somewhere in a piece of wood, then sometimes you need a washer. A washer is like a disc, but with the hole inside. That's what it means to be a washer. And so if you guys notice, if you didn't have the hole there, then this would have been similar to what you had with the disc, right? You have the radius of the big radius, and that would have been it, right? But because this is a washer, there is a small radius, right? Because that will be creating the hole. So to find the volume of this washer, if you guys think about it, it kind of makes sense to find the area of the whole thing, and we can do that by using the volume of a cylinder, and then minus the volume of a disk of radius r. Right? So find the radius of the big disk minus the radius of the small disk will give us the area or the volume of a washer. So pretty much what we're saying is that, right? R squared W minus pi R squared W. But we know that they all have pi and R, and pi and W are the common factors, so we can factor pi. And then we see that they both have W as a common factor, so we can factor W as well, right? And so that's how we can find the volume of a washer. Now, the volume of a washer is sort of interesting because it's actually allows us to find the area of objects that are not as simple as the disk. In fact, we're going to rely on the concept of the inner radius versus the outer radius that we have defined before. If you think about it, this will create an inner radius, and this will refer to as the outer radius. The inner radius will be created by the bottom part of the function, and then the outer radius will be done by the outer part of the function. So if you guys think about this actually this looks like this, and it has a special shape, and this is the outer, and then this is the inner. So when we find there's going to be also a rotation. So we're going to rotate this, right, into some axis of rotation. And this is how it gives us this volume. So we're going to rotate this part, and this is going to give us this solid. Well, it's sort of kind of everything connects together, right? If we try to find the volume of this washer for infinite n, then we end up getting similar concept as before. We're going to have r squared minus r squared. The pi is going to be factored out, and then w happens to be the width, which happens to be your delta x. So that's where it's coming from, right? So that's the washer method, and it's very once we know the formula, then we can actually do any problem that we want, right? So let's try the first one. Using the washer method, find the volume of the solid formed by revolving the region bounded by the graph y equals square root of x and y equals x squared about the x-axis. Again, the word about x-axis tells us the rotation, it happens on the x-axis, right? All right, so that's a subtle hint there. And so what we're going to do is, since we're rotating on the x-axis, that means that this being closer to the x-axis becomes the inner radius, and because this is further away to the x-axis, then it becomes the outer radius. Either you call it the big radius or the small radius. And then we're gonna recognize here that we're integrating from the furthest away that region can get is x equals 0, and the furthest the region can get is x equals 1, right? So that means that our boundaries are between x equals 0 and x equals 1. So here we go. Don't forget the pi from a to b, big radius square minus small radius square, pi 0 to 1. The outer function is square root of x square minus the inner function is x square, and that simplifies to be x, and that simplifies to be x to the fourth. Then we're gonna simply integrate by using power rule, and then we evaluate at 1 and 0. And again, like I did before, I'm gonna leave the pi outside, and I'm just gonna put a big bracket telling the reader that I'll multiply the pi at the end to everything. So then I'll plug in 1, 1, 0, 0, and that will become 0. So I'll just have to simplify this, which is just 5 minus 2 over 10, and multiply by pi gives me 3 pi over 10 units cubed. All right, so we know what to do here. We already know what to do here. Once it's set up, you guys are good to go, right? What I'm trying to focus here is the setup, and I want you guys to really think about that concept. Now, this can be extended to any axis of revolution. We could have extended this to, if I ask you that is about the y-axis, then that means the revolution would have happened over here. In that case, this would have become the outer function, and this would have been the outer radius, and this would have become the outer radius, this would have become the inner radius. So it's always in respect to the axis of rotation. All right, so next example we have we're integrating with respect to y. We have two integral cases that we're going to have to deal with, and we're going to talk about why it makes sense for us to separate it. And so to find the volume of the solid formed by revolving the region bounded by the graph, y equals x squared, y equals 0, x equals 0, and x equals 1 about the y-axis as shown in the figure. So if you guys notice, we have a rotation here. We know the region is bounded by the parabola, is bounded by this y equals 0, is bounded by x equals 0, and is bounded by x equals 1. So this is the region, and it's going to be rotating on the y-axis, so we're going to see this, right? We're going to see this. So so if we're using this, that means we are stuck using the vertical approach, right? And so we're going to have to deal with what is going to be the outer function, what's going to be the inner function. Again, the region that we're trying to cover is here, right? So that means that if you notice, the outer function will be this, and then the inner function will be this. But behold here, when you're trying to find the boundaries between the boundaries of y, of delta y, the delta y will be between 0 and 2. And if you notice, there is two different lower radius, this and then this. So that's sort of a problem, right? It's not gonna be able to fit in one single integral. So it kind of makes sense to for us to split it into two different regions, because they both have different inner radius. They both have the same outer radius, but they have different inner radius. So we're gonna separate it from here, right? We're gonna deal with this separately than with this. That's why we're gonna deal with this part first by saying, okay, sorry, we're gonna deal with this one first. From a big radius, from outer radius to small radius, right? We have big R is 1, little r is 0. and that's going to go from y equals 0 to y equals 1, right? Your delta y, right, is going to go from 0 to 1. And then from 1, we're going to go from 1. And then for this one, the outer radius is going to be 1, and the inner radius is going to be this function. Now, we do have to make sure that we write this function in terms of r, right, and y. So you got to write this in terms of y. So this right here happens to be your r, and so we're gonna solve for r by subtracting one, and then square rooting both sides, right? And that's how we got this one right here. So anyways, so now we have everything we need, and we're gonna go from there for 1 to 2. And so we're gonna have the setup, right? Now the volume will be, for the first one, will be from pi times 0 to from 0 to 1, outer minus inner dy, plus the second part, which will be another volume, pi from 1 to 2. Outer is 1 minus inner is this, right, in terms of dy. And then everything is very consistent now, right? We're gonna simplify this to be 1, simplify this, this becomes 1, and this becomes y minus 1. Simplify those two, and that will give us negative becomes plus, so 1 plus 1 is 2 minus y. And then that will give us this, and then integrate each one independently. So this will give us a y, this will give us 2y minus y squared over 2. Don't forget the pi. And then we're gonna do this one first. So pi, plug in 1 and then 0, plus pi, plug in 2, and then minus plug in 1, right? And then you'll simplify those. So we're just doing this independently of each other, right? This is that one, and this one is that one. So you're just doing each one independently of each other. And then this will give us just pi times 1. This will give us 4 minus 2, 2 minus 1/2, and we'll simplify that. This will give us negative 4. This will cancel each other out, so we're left with negative 1, negative 1/2. Let me see here real quick. Pi is that one. Oh, I did this, and then I did that. Oh, sorry. So this is 4 minus 2 is 2, and then 2 minus 1/2 is negative 3/2. Combine those two, and that gives you 1/2. And then combine those two, and that'll give us 3 pi over 2. So the volume of this is 3 pi over 2 units cubed. So there you go. We found the volume of the solid. So very interesting, right? The concept here, the point here is we are allowed to split the regions into our convenience, right? Just to make the problem much easier for us to set up. That's what I want you guys to focus, right? You should be using rational conclusions or rational steps to make this as simple as possible. All right. So moving on to the next part, we're gonna go ahead and find the integral of this solid. And so the practice 5 is asking us to if we have a manufacturer drills a hole through the center of a metal sphere of radius 5 inches as shown in the figure. The hole has a radius of 3 inches. What is the volume of the resulting metal? So we can see here the picture, right? We can see the picture that this we're going to be rotating about the x-axis because that's where the symmetric is happening. So another way we can think about, right, symmetry tells you where the axis of rotation is happening. So we can see that this is sort of like the region that we're going to be rotating. We're going to rotate it, and it's going to give us this whole thing. So we see here that we have the outer function and then somewhere in here we're gonna have a line crossing over from the drill. We don't know exactly where this. They did say that this drill has a hole of radius of 3, so we know this is 3. And we're gonna rotate it, right? We're gonna rotate it. So first of all, it looks like everything is set up here, right? We have the outer, we have the inner. The only thing that we don't know is what are the boundaries, -4 and 4, right? And we can see here that the boundaries are going to be at those two, but we also can find those two by setting these two equal to each other, and that would give us 4, -4. So we have -4 and 4, pi outside, don't forget about pi, the outer radius square, the inner radius square, and then simplify. This becomes 25 minus x squared, this becomes 9. Simplify those two, gives us 16 minus x squared. And then now that we're ready to, once you simplify it, now we can integrate. And that will give us 16x minus x cubed over 3 from -4 to 4. And then evaluate by plugging 4 and then by plugging -4. And so that's the 4 case, and this is a -4 case. Don't forget about the minus. The pi is outside. We're going to multiply that at the end. And so this will give us 16 times 4 is 64. 4 to the third is 64. 16 times -4 is -64. -4 to the third is -64. With the minus in front, it will give us positive. Combine like terms, you guys can see here that this will become negative. And so these can be combined to be -28 over 3. This can be combined, and that will give us positive 128. Combine like terms by multiplying this by 3, divided by 3. This will give us 384 minus 128 over 3. And this will simplify to 256 over 3 times pi. And so this is the volume of the solid. And that's it, right? So very consistent with what we've done before. All right, so moving on to the next part, the solids known from cross sections. We are going to extend this to, we're going to use the next technique to help us extend the concept of finding the volume of a solid. So with this method, you can find the volume of a solid having a circular cross section whose area is pi r squared. This method can be generalized to solids of any shape, as long as you know a formula for the area of an arbitrary cross section. Some common cross sections are squares, rectangles, triangles, semicircles, and trapezoids. So what we're saying here is, if you guys think about it, we were sort of finding the area of a, if I go back up here, if you guys think about it, we were sort of finding the area of the region and then sort of like extending it, right? So that same concept over here that we can use for any solid. So we can find the volume of any solid with known cross sections from sections from the area AX taken perpendicular to the axis. So what we're saying here is that if we know the area of a region, for example here, if we know the area of this plate, right, then what we can do here is, once you find the area of that plate, then you can just extend it from A to B, right? We can extend from A to B. Another way we can do this is also different perspective. If we actually know, again, the plate, the area of the plane of this plate, then we can just go back and forth between C between Y, which is C and D. So these boundaries, right? So once you find the area of the plate, right, then what we're saying is you can sweep from A to B, and that will give us the volume of the shape. So that's kind of what we discussed in the last time here. That's sort of kind of what I was trying to make the point on over here is, if you know the height of something, right, of this rectangle, if you know that the area of this rectangle, then what you do is you sweep around, right, from the -2, you sweep around, and by sweeping this, you're sort of collecting this area. And what I mean by sweeping is you're taking the integral from the start to -1, from -2 to 0, from -2 to 1, from -2 to 2. So you're sweeping from -2 to 2. And it's the same idea over here. Is once you find the area of this rectangle, then what you're doing is you're sweeping from A to B, right? You're sweeping from A to B. Instead of you're automatically collecting every single step that you take, you're collecting the area of the solid. And again, it follows the same idea. If you have the rectangle, the area of this rectangle, and you sweep from C to D, then you're finding the area of the solid. So that means the volume of the solid. So it's sometimes the trick here is to find the area of the plate, and then after that, then you just have to put it in the integral, right? Just find the area of the plate, and then just sweep, and this represents the sweeping part. This represents the sweeping part. All right, so the next example, we have a triangular cross section. Find the volume of the solid shown in the figure below. The base of the solid is the region bounded by the lines 1 minus x over 2 and g equals -1 over x over 2 and x equals 0. The cross section perpendicular to the x-axis are equilateral triangles. So here we go, right? So here we have the shape of the graph here. This is a three-dimensional solid described in a rectangular coordinate system. This means that you have a z coordinate coming out. So here if you think about it, this part right here is your g, right? Which is where is my so we have -1 means our intercept is lower, and then we have a slope of 1 over 2. So we go 1 up, 1, 2 to the right, and that gives us this line right here. And then over here, this gave us the intercept is 1, so move 1, and then the slope is -1/2, so go down 1 and then run 2. So that gives us this line over here. So on the xy axis, we see this triangle right here. We see this triangle, and our goal is to find the area of this solid, and it's also bounded by x equals 0. So we're bounded by this. So we're sticking on this side of the graph. And then on the top we have equilateral triangles. So what we're gonna do here is our goal is to find this area, and then sort of use the same concept of sweeping. So what we're gonna do here is find the base of this region. So we have our base is described by subtracting these two. So if we subtract this from this will give us this height right here, right? This will give us this height right there. So subtract this with this will give us this height right there, which is described as 2 minus x. Now, why does it depend on x? Because it depends on where your x is. The difference between those two is going to be different, right, for every x. So it depends on x. It kind of makes sense. Then what we're going to do is, once you know the width of those two, then what we need to figure out is the height. What is the height of this? Now we know that's an equilateral triangle, right? So we know that this is going to be, we can figure out this height. And to figure out the height, we can multiply it by, I'll jump in a second with that part right now. Let me just focus on if we know the height of it. Okay, let me first do the problem, and then I'll explain where we got the height, right? That way we can still focus on the main part, and I'll show you guys. The other step is just an algebraic, simple algebra step, but it's gonna take me a few steps to explain it. So once you figure out this height, which happens to be the square root of 3 over 4, then all you gotta do is multiply the height by the base, and then divide it by 2, right? And that will give us this part of the area. That will give us this area. So once you find this area right here, then what you're gonna do is you're gonna sweep from x equals 0 to x equals 2. So that means because x ranges from 0 to 2, the volume of the solid is going to be described as the volume from A to B, ax dx. There's no pi here, right? Because you're not dealing with rotations. And then so you're gonna replace this with your area, and again we're gonna explain how we find that. And it works for any area, right? In this case it happened to be a triangle, but it works for any area. Notice that we're gonna have to do here u substitution. So this is gonna be my u, and my du is gonna be negative dx. So I'm sort of missing my negative, so I put it there and then compensate it outside. Now by u substitution, this becomes u squared, and this becomes du, and then and the negatives now carry outside. Do the integration. This will give us u cubed over 3 times negative square root of 3 over 4. From 0 to 2, we cannot plug in 2 yet because this is in terms of u, so we got to turn this back into x. 2 minus x, and then to the third over 3. And then now finally we're going to plug in 2. So 2 minus 2 cubed over 3 minus 2 minus 0 over 3 cubed, right? So we plugged in those two here and here. This one, again, you can just put a big bracket and then worry about this product at the end. That way you're not dealing with this so many times. So therefore we're going to get 0 for this, obviously. And then this one will be 2 minus 0 is 2. To the third is going to be 8. So this is 0, so we have negative 8 thirds times negative square root of 3 over 4. That gives us this. The negatives will cancel each other out. 4 goes into 8 twice. And so we end up getting 2 times square root of 3 over 3 units cubed. And that's pretty much it, right? So the idea is, if you can figure out the height of the area of the plate, then you can figure out by sweeping this, you can figure out the volume. So now let's figure out the height of this, right? Or the area of the rectangle. So here we go. All right. So if you picture this right triangle, picture the right triangle. We already figured out that this right here, this right there. Let me put this in red. This right there is 2 minus x, and our goal is to figure out what is the height, because that will help us find the area. And so to find the height, we have to think about the fact that these two are going to be equilateral. So that means that that half of this right here, this is half of this. So that means that sorry, that's not actually that's not correct. Sorry. All right, so we're trying to figure out the height. We know this part right here is going to be half of this, and thus we're gonna try to find this part over here. This part right here is equivalent to this side over here because it is known to be an equilateral triangle. So what we need to figure out is this part right there. So this is what we're trying to figure out. So let me translate the problem to be this little triangle. So this is 2 minus x. This is what we're trying to figure out. And then this is not this whole thing is 2 minus x, so this will be half of that. So it'll be 2 minus x over 2. And then we're gonna go ahead and find the area of this. So how do we find sorry, we don't have to find the area. We're finding b. B is the height, and so we're gonna do Pythagorean theorem. So it'll be b squared equals 2 minus x over 2 square equals to 2 minus x square. All right, and we're gonna go ahead and square that. and that's going to be again, sorry, that's going to be plus equals to same idea. All right, and then we're going to subtract those two on both sides of the equation. And they're going to need common denominator, so I'm going to multiply this by 4 and divide by 4. So if we multiply by 4, this will give us 16. And then minus this whole thing. So I just changed the sign. This will give us 12. This will give us 12. And then this will give us 3x squared. And then this will give us and then we can factor 3. And then let's see. So, oh yes. Okay, and then we'll do the square root on both sides. And there you go, right? So we end up getting that b is going to equal 3 square root of 3 over 4 of x minus 2. So then that will give us our b value, and that will give us the number that we're looking for. All right. So anyway, so that was so that's how we found the area. We could the point of this is, again, finding the area of this plate and then sweeping around, right? And sweeping around, and that will give us the area of the volume. All right. So I hope you guys find this helpful. Please let me know if you have any questions. Or until next time.